Okay, so I'm going to start by, are you ready?
I am.
Okay, so I'm going to give an introduction to Chabauty's method, and actually, even before I do that, let me say what some of the motivation for it is. That's okay. I mean, if you want, I can remove them. All right. Now is everybody happy? All right. Okay. So let me first. I mean, the idea is try to find rational points on a curve. So let me first talk about that problem. So rational points. All right. So the theorem that we all know, I think, is Falting's theorem. And well, I was told you're supposed to put an extra S on it. Okay. So Falting's theorem, which was originally the Mordell conjecture. Which was conjectured. This was conjectured back in the 1920s, and finally proved by Faltings in 1983. So this says that if you have a number field, so K is a finite extension of Q, and then you have a X is a well, I'll just say nice curve. It's a nice curve of genus G over this field, over this number field. Okay, so nice means, well, okay, so let's see. This is just an abbreviation for, well, everything nice. So smooth, projective, and geometrically integral. So which means that it stays irreducible and reduced even after you base change to K bar. All right, so those are the hypotheses, and then if the genus is greater than 1, then the set of rational points is finite. Okay, so this is the statement, and there are several proofs now. So there are proofs by, first of all, it's called Falting's theorem, and there's a reason for that. It was proved by Faltings, this was in 1983, and this was via Arakelov methods. Okay, I'm not going to try to explain his proof, but all these proofs are kind of difficult, so it would take many lectures to go through any of them, I think. So, okay, and there's then later Paul Vojta gave a proof, published in 1991, and there's also a variant. There's a variant by Bombieri. That's a more it's in some ways it's kind of the same proof, but it's more he managed to rephrase it in more elementary terms. So, all right, and this is via Diophantine approximation, and then recently there's a third proof. This is by Brian Lawrence and Akshay Venkatesh. So, well, I don't know if it's published yet, but there's a preprint is dated 2018, so I'll just say 2018 plus, where it's like a plus epsilon, where we don't yet know what epsilon is. So, okay, so this is via p-adic period maps. Okay, so I'm not going to talk about any of these proofs. I don't know even why I'm writing all this stuff, but anyway, there it is. Okay, so that's for rational points. Now there's also an analog for integral points on affine curves. So let me state this as well. So for integral points, so there you can. So the analog of Falting's theorem is Siegel's theorem. All right. So. And here the setup is, well, again, you have a number field. But now we're going to look at either the ring of integers Or more generally, you could talk about the ring of S integers. So O is going to be OKS, where S is, so this S is going to be a finite set of places of K. And I'll just for simplicity, I'll assume that it includes all the Archimedean places. So all the real and complex places. Okay. So so what is this ring? It's I mean, you impose integrality at all the places outside S. So it's the set of X and K such that the valuation is, so it's integral for all V outside S. Okay, so that's the ring of integers, and now we need a curve, and except it's going to be an affine curve this time. So let's call it U, and well, it's going to be a smooth affine curve, so it's going to look like it'll look like a nice curve. Okay, so this is nice curve of genus G, and then we'll remove a finite subset of points. And so, well, you can think of it as a, let me just say it's a non-empty zero-dimensional subscheme. Okay, so it's if you prefer to think over what it looks like over K bar, then it's just a finite it's just a finite set of points that's being removed. And okay, so all this should be defined over K. So, and by that I don't mean that the individual points in Z have to be defined over K, but I mean you could also think of Z as a Galois stable subset of the K bar points, because that would be something that descends to a zero-dimensional subscheme defined over K. All right, so. And now, I mean, to state, I mean, in Falting's theorem, there's this condition that the genus had to be greater than 1, and the analog here is expressed in terms of the Euler characteristic of this curve, which is defined as follows. This is the topological Euler characteristic, and you start by taking the topological Euler characteristic of X, which is 1 minus 2G plus 1, which gives you 2 minus 2G. That's the alternating sum of the Betti numbers. And then every time you remove a point, every time you remove a geometric point, you decrease it by 1. So this is going to be, so I'll subtract from this R, where R is the number of geometric points of Z. So it's the number of points here. Okay? So now, finally, we want to talk about integral points on U, but U is a scheme over K, so strictly speaking, it doesn't make sense to talk about integral points. So in order to talk about integral points, we need to choose a model for U over O. So let me call that fancy U. Okay, so that's going to be, yeah, I don't know. I mean, I know that some people when they have a fancy X, they call it X, like this guy here, and like it's a French X, so it's like fancier than a usual X. But it doesn't work so well for U because it's an E or something. I don't know. So I'll just call it fancy U. So, all right. So anyway, what is it? It's a finite type. It's a finite type O scheme. So that's kind of. I mean, you can assume it's separated if you want. I think it doesn't really matter. But so this is like the analog of a variety over a field, and it should have it should be somehow related to the original U. So it should have if you take its generic fiber, so you base change to capital K by taking U cross spec K over spec O. That should give you back the original U over K. Okay, so now the statement is that if the Euler characteristic is negative, so this is the analog of this G greater than 1 condition. So you can see that in the case, well, if R were 0, then that this Euler characteristic negative would be saying that G is greater than 1. And so then, so then the conclusion is that the set of integral points on this is finite. Okay, I guess Siegel probably didn't state it exactly like this, because I mean this is from 1929, and he probably didn't know what a scheme was, or at least if he did know what a scheme was, he wasn't telling anybody. So okay. So by the way, another thing, this condition, this inequality that says that the Euler characteristic is negative, this thing, sometimes people also will say that this curve is, this affine curve is hyperbolic. And yeah, I think the reason for that is just that if you take, if you're working over the complex numbers, and you have such a curve, and you take its universal cover, which maybe I'll just put a tilde on it, then for such a curve, the universal cover is isomorphic to the hyperbolic plane, which is like the upper half plane in the complex numbers or the complex unit disk. So I think that, okay, so anyway, so that's, so it carries a metric of constant negative curvature and stuff like that. All right, so again, so you can talk, so this is the statement. And there are several proofs. So maybe I'll say, so first of all, so there's a proof by Siegel. So this is in 1929. So via Diophantine approximation. There's also partial proof by Alan Baker and John Coates. And this was from 1970 now. And this one only works when either G is at least 1, or sorry, G is less than or equal to 1, or the curve is y squared equals f of x. It's a hyperelliptic curve with the points at infinity removed, and that would be inside A2. So, but the nice thing about this proof is that it's the only proof that's effective. So this proof actually gives you a method. It gives you a bound on how large the integer solutions are, the integral points. And so not only is it finite, but you can actually write down all the integral points. Whereas in the general case, even for other kinds of curves, there's still no known algorithm. Okay, and then again, recently, this Lawrence and Venkatesh, sort of independent of their proof of their new proof of faulting theorem, they also showed how you could use it to prove this. And they wrote it out very explicitly, in fact, as a warm up for this one, in the case where, so this is at least they did it for P1 minus 3 points. So when U is P1 minus 0, 1, infinity. Okay. All right. So those are the proofs that are known. And let me just say a few things about some relationships between these. Actually, maybe before I do that, let me just do this last example. So as an example, if you take the case where U is P1 minus 3 points, and fancy U is also P1 minus 3 points, except now over O. So so I guess if I want to write it out explicitly as an affine scheme, I would take spec of O, and then that would be A1. That's P1 minus infinity, and now I remove 0 and I remove 1. So that's U, and then if that's what fancy U is, then the integral points, those are going to be, well, they're going to be certain integral points on A1, but more precisely, if I Actually, I'm kind of regretting writing x minus 1. I think I prefer to write 1 minus x. Okay, I know it's the same ring. But, I mean, now if I call 1 minus x, if I call that y, then I can think, well, then x plus y is equal to 1. And so, but then x and y are both required to be invertible. So these are the same as, so the integral points are the same as the solutions to x plus y equal 1, with x and y being units in this ring. So this is sometimes called the unit equation. So the integral points on P1 minus 3 points is the same as the unit equation. Okay, so that's an example. And let me make another remark. There's some relationships between Siegel's theorem and Falting's theorem. So in some sense, Falting's theorem is harder in that if you can prove Falting's theorem, you get Siegel's theorem almost for free. And this is the key behind this is the observation that if you start with if you're trying to prove Siegel's theorem, so you have your u that's hyperbolic, then it has you can find some finite étale cover. So of the curve, of the affine curve, that is open inside a curve of higher genus, inside it's open in a nice curve of genus greater than 1. And so if you know that and you know descent theory, then you can reduce the problem of finding integral points on U to the problem of finding the integral points on this cover, and maybe some of its twists. And then, well, those are going to be contained in the rational points, and so the rational points are finite by Faltings if the genus of the covering curves is large enough. So okay, so anyway, that's a nice. So yeah, so you don't need to worry about Siegel's theorem, just prove Falting's theorem, and then it's all fine. So another thing is, so let me go back to, well, okay, I guess I don't know if you can see both of these, but okay. All right, anyway. So if you look at this, actually, let's look at Siegel's theorem. Let's look. Sorry, I just. Too many places to put paper, sorry. Okay, so let's look at Siegel's theorem. Now here I assume that Z was non-empty, but do you know what happens if you let Z be empty? So that means that U is just the same as X, and X is a projective curve. So if you look at the integral points on a projective curve, then the validative criterion for properness will tell you that the integral points on a projective curve, or anything proper, will be the same as rational points. And so then the set that this is claiming to be finite would say that the set of rational points on the curve would be finite. And then this hyperbolic condition is the same as the one in Falting's theorem, saying that the genus is greater than 1. So then this theorem would specialize to Falting's theorem in the case where Z was empty. Although I assume that Z was not empty, so it doesn't actually specialize. But so if you want to, you can take this thing. I'm not sure if I'm allowed to do this. Am I allowed to modify my? I guess I shouldn't modify my paper because it's going to be recorded.
I mean, it's just going to record the modification. So.
Oh, but you don't. But you're going to scan these things, right? And it doesn't matter. Okay, well, let's just pretend. Okay, let's just pretend that we are modifying it. So I'll take this red pen. I won't actually take the cap off, but let's pretend I crossed out the word non-empty. And then yeah, that's all. I just cross out the word, and then I put a hyphen here. I get rid of the apostrophe s, and I put hyphen Faltings. And then you get the Siegel-Faltings theorem, which is like a combined statement that includes both the Siegel and Faltings theorem. So you can do that if you want. Okay, and yeah, so maybe I'll just say, as far as that goes, in that version of it. Okay, so now I'm. Okay, so I'm using the red pen, so this is now Siegel-Faltings. Okay, so if in the Siegel-Faltings, So then this condition that the Euler characteristic is negative, this hyperbolic condition, concretely what it means is that, you can just write out what it means. We have the formula. So either G is equal to 0 and R is at least 3. So it's like P1 minus 3 or more points. Or you could have genus 1 and then you have to remove at least 1 point to make it negative. Or you could have G at least 2 and R could be arbitrary. So yeah, so the middle case would be like integral points on elliptic curves, where by that, of course, you mean you remove a point, say the point at infinity. Yeah?
What do you mean by the same finite cover is open?
Oh, that says, okay, this is a problem with the pens. That word is not same, that says some. I'm saying that some finite cover is open. Yeah, okay. Any other questions? All right. So okay, so now I haven't talked about, so as I said, the problem with all these methods is that none of these are effective, well, except for the Baker-Coates method, none of these are effective. So the big problem is to develop new methods or to develop old methods that will actually find the rational points. If somebody hands you an equation, you want to actually write down the rational points. And so this is what Chabauty tried to do a long time ago. So let me explain what Chabauty's idea is. And his method was based on an earlier, this is a p-adic method, and it's inspired by an earlier p-adic method by Skolem, who used it to study things like the unit equation, which is like the integral point analog. But I'm going to state the version for rational points. So let's talk about a field extension, k over q, as in Falting's theorem. And let me choose a prime. So it's going to be p-adic method, so I need a prime, and I'll choose a prime upstairs as well. And I'll need a curve. So let's say x is a nice curve of genus G over k. Let's say, and let me assume that it has good, just for this, let me assume it has good reduction at the place P. Actually, I think maybe for what I'm going to say, it doesn't really matter. But yeah, actually, I think it's okay. Let's forget that. I think I can get. Let's not even bother with that. Okay, sorry. So it makes things a little bit easier if you're actually doing the calculations. But I think for what I'm going to say now, it's not really required. Okay, so let's take J to be the Jacobian of this curve. So what is that? So that's going to be that'll be some G-dimensional abelian variety, where the G, where the same G, the G is the genus, and then you can talk about the group of rational points of that, and as for the Mordell-Weil theorem for elliptic curves, the group of rational points is finally generated. It's a finally generated abelian group, and so you can talk about its rank, which I'll call R. And, maybe that R was a bad name because it was. Anyway, this is a new R. So it's not the number of punctures as it was in the previous slides. There are no punctures here. This is a nice curve. So, okay. So, all right. So, if I want to draw this, I would do something like, let's see.
So x is projected here?
Yeah, that's part of what nice means. Yeah. So x is smooth projective, geometrically integral. So let's see. So let's draw a box. So I can't make up my mind which color to use. So maybe I'll just use black. Okay. So it's a p-adic method. So we're going to look at J, the sort of the p-adic manifold of points, or p-adic Lie group of points over. That's k sub p. That's the completion of k at p. And then inside there you have the Mordell-Weil group, which is going to be a finally generated abelian group. So it's a point and all its multiples. So I'll write that'll be J of k. And then you also have the curve itself, maybe I'll put a couple more points in there. Actually, if it's infinite, then it'll be dense in some kind of, I mean, if you take, just because this thing has an open subgroup that looks like a power of ZP, if you take integer multiples of a point, they won't like go off, they won't be discrete. They'll be like taking integer multiples of a number in ZP. They'll be dense in some kind of interval, quote, interval. So you'll get some kind of thing like this. If you take you could take the closure and you'll get some actual analytic subgroup that's actually another manifold. Okay, anyway, you can intersect that with let's see. So let's take with the set of points on the curve itself. So let's say this is a analytic submanifold, the set of local points on the curve. And the point is that all the k points of x must lie on both of these. They must map both to, okay, so maybe I'll make a little diagram here. So x of k must map into, it's a subset of the kp points. On the other hand, it must also map into the group of points in the j. So I guess implicitly here I'm choosing a base point in order to choose an Abel-Jacobi map and embedding. Yeah, maybe I should write that. So let's say, okay, let's assume there is a point. So x to get x contained in j. And so then, yeah, so then the rational points will map to rational points, and this is all happening inside this ambient, this p-adic Lie group. So you have, yeah, so, and so then this diagram, I mean, this shows you that the rational points of the curve must be in the intersection of the local points and this Mordell-Weil group. And so that's the idea, to try to compute the intersection of these two things, and you hope that the intersection points are actually the k points and there's not extra stuff in there. Now, if you're actually doing this in practice, it's hard to do the calculations because the group law, I mean, writing on j of k is kind of difficult because you have to use the group law of the Jacobian. And I mean, the group law on an elliptic curve is bad enough if you try to write down in terms of rational functions. If you've ever tried to do it on a two-dimensional variety, I mean, actually even just writing down what the Jacobian is as a projective variety is kind of nasty. And writing down the group law, it gets really nasty. So you don't want to actually do that. So instead, what people do is they use the formal logarithm map that's obtained by integrating one forms p-adically. So there's a map we'll call log that goes, well, okay, canonically, it goes to a vector space of the same dimension as j. So, but yeah, canonically, it's actually the Lie algebra. So of j, except j base change to kp. So this is actually a copy. It's just a g-dimensional vector space over this local field. And the nice thing is, after you apply this on the right-hand side, on the group law gets transformed into addition, and everybody knows how to do addition, especially in a vector space. So yeah. So, okay, good question. So what's the difference between this j of kp and j sub kp? So when I write j sub something, I mean I'm taking the base change of it. So that means that j is originally a abelian variety over k, and now I'm considering it as a variety. This is a variety. This is a variety over kp. When I write j parentheses kp, I mean I'm taking the set of kp points of j. So this is just a set, well, actually a group, but this is just an abelian group where this is an abelian variety. This is a variety. Okay? All right. So yeah. So the idea is, instead of trying to compute the intersection of these two guys in here, so these two things mapping into here, I will just push everything forward over to here and try to compute their intersection of their images over here. Inside this little vector space where things become easier. So in particular, the Mordell-Weil group becomes easier just because I have maybe R generators. Yeah, by the way, the torsion subgroup here is going to get killed because, well, I mean, there's no torsion in here. So where could it possibly go? So yeah, so so maybe I can say a little more about what's going on here. So this logarithm map is close to being an isomorphism actually. The kernel of this log map is finite, first of all. In fact, the kernel turns out to be exactly the torsion subgroup of this, of the group of Lash. And also, you can say something with the image. Log is actually a local diffeomorphism, and because of that, the image of log is going to be, and it's a homomorphism, so the image is going to be, well, first of all, the image is going to be open, but it's also going to be compact because this is J is projective, so this is a compact group. And so the image is actually a compact open subgroup of this vector space, of this p-adic vector space. I mean, it's not necessarily an OP module where OP is the valuation ring there, but at least it's a ZP submodule here. That's a full rank. It has the same rank as the whole vector space. So yeah, okay. So and also from this you can say, well, if you take the J of K and you map it across, and then you take, yeah, so you could take the image of J of K under this log map in this vector space, and that's going to be generated by it's generated by R elements, namely the generators of J of K, because the torsion is going to disappear, as we said. So therefore, I mean, you have R elements then that generate this subgroup here, and so they're going to be contained they're going to span a subspace here. That's at most R-dimensional. So let me write that. So the dimension of KP, as a KP vector space of the KP span of this same image. Maybe I won't write it again. Is going to be less than or equal to R. Okay, so now that's good news, because so now what happens is that if the rank is less than the genus, well, then the span is not the whole space, and therefore you can find a linear functional that vanishes. There's going to exist a non-zero linear functional that vanishes on this image of the Mordell-Weil group. So there exists a non-zero linear functional lambda that goes from, well, maybe I'll use the canonical version, from this G-dimensional vector space to KP, and that vanishing on the image of the Mordell-Weil group. And so now what that means is you can, well, so you have now a linear functional in the whole space that zero on J of K. So now you can just restrict that to the curve, to the local points in the curve, and so when you do that, so in other words, you pull it back to the curve to a non-zero locally analytic function. I mean, it's analytic because this log map is only analytic. It's obtained by integrating a power series. Okay, so it's a non-zero locally analytic function. It's sort of analytic on each residue disk. Okay, so it's a locally analytic function, and this function, well, it's on this one-dimensional KP manifold, and this function is vanishing on the set of rational points on the curve. And so, yeah, and because, I mean, if you have a locally, so power essentially on each residue disk, it's a power series. Then a non-zero power series in a one-dimensional space has only finitely many zeros if it's a little compact on a closed disk. And so on each closed disk, this function will have finitely many zeros, and therefore x of k itself.
Can you write higher?
Oh yeah, good idea. Okay, so x of k itself is finite. Okay, so that was, yeah, so that's Chabauty's idea. So, but you see that there's the key condition here is there's a big if here that you need this hypothesis. And so that's maybe Chabauty's condition. And if you didn't have that, then it could be going back to this picture. You would have the same kind of picture, except now these purple dots would be could be dense in the whole group. And then it's really hard to figure out where they intersect the curve. So the method just doesn't work at all, as stated. Okay, so now let me start moving towards towards Kim's generalization. But before I generalize it, let me say how you can restate this without mentioning Jacobians. So this was the first step that Min-Young Kim had to take in order to generalize this. So, because you notice if I go back to here, there's Jacobians all over the place. There's there. Anyway, look at all the J's on this page. So we want to get rid of all the J's. Okay, that's the idea. So how do you do that? So the goal is get rid of J in order to generalize. I mean, the hope is that the generalization might be more applicable in situations where this hypothesis doesn't hold anymore. So that's why we want to do this. Okay, so let me now start over. Well, not completely start over, but I'm going to start by copying. Okay, so this is the rewriting. So rewriting so as to eliminate J. So we're going to start with the same diagram here, this famous Chabauty diagram. And so I have this mapping to X of Kp, and then this maps down to J of K, and over here you have J of Kp. And you have a big horizontal map here, and you have the log that went to the Lie algebra, which really we're just thinking as a vector space. I mean, it's a commutative, so the Lie bracket is 0. Anyway, don't worry about I just wanted to say some way of this. I really just want to talk about the tangent space of the identity. That's all this is. So that's just a G-dimensional space. And so the first thing I'm going to do is take a p-adic completion of these groups. So there's going to be a group here that I'm going to write as G of K. I'll explain what this notation means in a second, and I'll also want to invert P, and I'll do the same thing here. Okay, so right. So what are these things? So maybe I will. Okay, I'm going to go back and forth between these diagrams and defining things. So over here, let me define what I mean by, in general, by p-adic completion. So if you're given, say, M, which is an abelian group, so there's always something you can do to turn it into a ZP module. You can define the p-adic completion to be, well, you take M modulo Pm, and you take M mod P the n M, and you take the inverse limit of those. And so those will be that'll be a module for the inverse limit of Z mod P to the n Z, which is the definition of ZP. So this thing is going to be a ZP module. And then if you don't like rings that aren't fields, you can change ZP to QP by adjoining 1 over P, by localizing. So you can so you can just take this thing and localize this module by inverting P. And so that, yeah, so that's, well, not defined to be, but it's isomorphic to M tensor and this M hat. It's the same as tensoring it up to QP. And so the result of that is a QP vector space. Okay, so maybe now I can go back to my diagram. So let's go here. So here I've taken the P. I mean this is a functor. Taking M to M hat is a functor, and localization is also a functor. So this maps, and so JFK maps here, and also there, I can also fill this in with a horizontal map here. All right, and then well, I guess I can also say that there's going to be an isomorphism here. That log induces an isomorphism here. Just that just because, well, because of the things I was saying before about the log of the map. It's almost an isomorphism already. The only thing that was wrong is it was compact open, and it had, I guess there's some torsion that got killed. But I mean, when you take the P at completion, you invert 1 over P. It's now going to be a QP vector space. There's not going to be any torsion left. And also, it was already spanning it was already spanning the space because it was a compact open in here. So when you complete it and localize to make it a QP vector space, it's going to map isomorphically. So yeah, okay. And so now everything's QP vector spaces down here. And so the next step is going to be to try to re-express everything in terms of étale homology. So maybe I think I'll need a new page for that. Okay, so actually let me put this into the diagram first. So what we're going to do next is we're going to, I mean, you know that if you're doing 2 descent on elliptic curves, say, you know there's a map from E of k mod 2 E of k into H1. It's like a Kummer map that goes into H1 of k comma E bracket 2. So there's going to be something, I mean, this is built out of quotients that look like that. This is things like J of k mod P J of k and stuff like that. So there should be an analogous descent map here into some Galois cohomology. And that's true. It will go into something, and it'll be something that I'll write as H1 of the Galois group of k acting on some kind of tape module. And then there'll be something. There'll be a local version of that too. So there'll be something I can put here. There'll be an H1 of the Galois group of the local field V. And so I want to explain what this V is. And then there'll be vertical maps going downward. And so this will. I mean the cohomology is supposed to make things easier. I mean, because it's easier in the sense that you don't have to deal with this pesky abelian variety. I mean, it's this thing with a complicated group law, because V is just going to be a vector space. I mean, it's the same reason that people use tape modules. You want to get something that's somehow just a linear algebra object, and get rid of the algebraic geometry. So, all right. So let's talk about that. So, all right. So what is V? So V is going to be you can think of it as sort of étale homology. I mean, I'll say what this means. By the way, I should have said, I mean, a lot of this rewriting, the exposition I'm following now, this exposition of Kim's method, I'm largely following an exposition that was given by David Corwin in some notes on his webpage. So if you want to know a lot of details, that's one place to look for it. So, okay, so let's see. So, okay, before talking about the étale homology, let's just talk about regular homology. So as motivation, so maybe motivation will be, I don't know. Look, here's a nice color. Okay, motivation. So let's work over C. So let's take X, a curve over C, and so it also has a Jacobian, and we know that over the complex numbers, just as elliptic curves are uniformized as C modulo a rank 2 lattice, the group of complex points here is as a complex manifold. It's analytically isomorphic to to a complex vector space modulo some rank 2G lattice. And that lattice, you can think of it canonically, I mean, it is the fundamental group of this space because the universal cover is, it's obvious what the universal cover is, it's C to the G. So this is the fundamental group and it's already abelian. So this you can also think of as the homology. It's the abelianization of the fundamental group. So it's the, with Z coefficients. Okay, so that's just usual algebraic topology kind of homology. And also in this, I mean, the point of this is a lot easier because here the group law is just plus again. And so, and you can also understand things like because the group law is so easy, you can also see what the p torsion corresponds to under this. Because it's easy to see on the right-hand side what the p torsion points are. They're just the points such that when you multiply them by p, they end up in the lattice, modulo the lattice. So, and then that's going to be isomorphic via multiplication by p to lambda mod p lambda, which you can also think of as being a kind of homology, except now instead of z coefficients, it's the homology with z mod pz coefficients. And then there's a final step that for a curve and its Jacobian, the homology the homology groups are the same. So at least for the H1 is the same. So this is the same as the homology of the curve with z mod pz coefficients. And now look what's happened. I got rid of the j. So there's no j here. So I can talk about the p torsion of the Jacobian without having a j in there. And you can do this not only for the p torsion, but you can do it for the p the n torsion and so on. And so yeah, so now let's do the analog for of that, but use for a curve that's not over the complex numbers. And so for that, we're going to have to use étale cohomology instead. So now let's go back. So now let's go to the real situation. So for x over the number field, so we'll talk about, well, you'll have j of p is going to be isomorphic to the H1 of, well, there's a notion of étale homology. And it's which if you want, you can just define as well, if you know what étale cohomology is, then you can define this one just as the dual vector space. So, okay, so this is supposed to be the analog of the previous isomorphism that I had over the complex numbers. And yeah, so as I wrote, this is just defined to be, it's just the FP, the Z mod PZ dual of the H1. Yeah, you always write H upper 1 for cohomology and H lower 1 for homology, and then you put the little étale wherever it fits. And then, yeah, and you always do to take étale. I mean, typically you normally take cohomology of the geometric object, so you always should base change to the algebraic closure before you take homology or cohomology. Okay, so all right, so you've got that. And okay, and likewise, you can do this, as I said, you can do this not just for p torsion, but you can do this for the p the n torsion, and so that will be isomorphic to the H1 étale homology, but now with the Z mod p the n z coefficients. And so, and finally, you can take the inverse limit of these. Okay, so let's do that. So I'll take inverse limits over n. And so that gives you the definition of the Tate module of J. So this maybe I'll call this one the ZP Tate module. And maybe I'll just call it T. So T is defined to be the inverse limit of these under multiplication, and that's isomorphic to, yeah, and I'm just thinking of these as subsets of the group of points over k bar. So this is just as an abelian group, and well, it also has a Galois action, which I'll mention later. But yeah, and so if you want, you can think of this as, you can define the inverse limit of these guys to be homology ZP coefficients. And then again, if you don't like rings that aren't fields, you can tensor it up to QP, and so you can get the QP Tate module. So yeah, so by just inverting P, so V will be T, where you just localize by inverting P, or if you want, you can think of it as being tensoring it up, tensor over ZP to QP, and then I can think of that also as an Atoll homology group, but now with coefficients in QP. Okay, and there's one final step that's going to be okay. So what kind of object is this? I mean, this is going to be some. I mean, this is just a vector space, and it's a QP vector space of dimension 2G. And you can also think of it as, I mean, actually later on it's going to be useful to think of this V not just as a vector space, but there's always a way to go from a vector space to an algebraic group whose points are the vector space. That algebraic group is going to be a sort of a stupid algebraic group. It's just going to be a power of GA, the power of the additive group scheme. And so I can think of, if I want to, I can make it a fancy V, and just think of it as the QP points of this. So I mean, this V, I mean, okay, so this is for a group variety, some algebraic group. That's where this V as a I mean, it's a power of the additive groups scheme, which is usually written GA. And so yeah, and this is over the field. It's a variety over QP. And more, I mean, what it is it's this thing is as a variety. It just looks like an affine space. It's just a 2G dimensional affine space. But you make it a group variety by defining the group law to be just addition. So coordinate-wise addition. So with the additive group law. Okay, so you might say, "Oh, why are you doing this stupid thing?" Well, yeah, it is kind of stupid, but it's going to be important later on. So, all right. And the last thing maybe I'll say about this is that the Gal group, the Gal group acts on everything. So the absolute Gal group of K, which is defined to be the Gal group of K bar over K, it acts on everything on this page. Well, just about everything on this page. Maybe it doesn't act on things like the word likewise, but it acts on most of the other things on the page. So this acts. In fact, it acts continuously. I mean, this is a profinite group, so it has a profinite topology. So it acts continuously on all of these, even on this variety, even on all of these. So it even acts on this variety. And I mean, you might think it's, well, I mean, even though the variety itself is over QP, this is a non-trivial action of this group that has, I mean, K is not related to this QP, but nevertheless it acts. And so for example, you get a homomorphism from this absolute Gal group into the automorphisms of this V as a group variety. The automorphism as a group variety of this curly V, which is just the linear automorphisms of this. So this is just a copy of GLN. It's isomorphic to GLN QP. Okay? I think this is a good place to stop. So I'm going to continue with this. So okay, maybe I'll just summarize where we are right now. So we just defined this V, and the point of this, going back here, was that this let us, well, I guess I haven't even defined this maps yet, but at least I've defined what V is. And notice that V, the definition of V, although it originally came from the Tate module, you can express it without talking about J. You can express it as this homology, which is just a localization of an inverse limit of duals of Atoll homologies, or duals of Atoll homologies. So it's all expressed in terms of X. So whenever you see a V, you can rest easy because V does not depend on J even. Okay. All right. So we'll finish. So after the break, we'll finish filling in this diagram, and then we'll the whole Chabauty, this row, which is the bad row, this one here, this bad part of the original Chabauty diagram will suddenly become green somewhere down here. Okay? All right. So so I guess it's break time.
We have a minute or two for questions if anybody has one they'd like to ask. Okay, if you could use the microphone so that posterity will hear you.
This is like ridiculous. I'm just asking for a clarification on what something says. Hi.
Yeah?
You have like ought, subscript.
Oh, over here. Okay.
Does that say QP variety?
So this here.
Ought.
So sorry, that says group. I was
I'm
running
sorry.
out of space at the bottom.
That's okay.
That's supposed to be a G. I don't know. I'm not going to try to fix it. It'll probably make it worse. But I'm just thinking of automorphisms as a group variety. So automorphisms that are also group they're both variety automorphisms and they are group homomorphisms at the same time. And so all those things are, V is just like an affine space, and these are just like the maps from affine, like A to the n to A to the n, that are where x1 comma x to the n goes to a tuple of linear combinations of things.
Bjorn, can you just move the last slide up a little bit? I think this side is visually blocked.
Wait, like higher? Wait, what's wrong? What?
Probably you should not sit here because this isn't going to change. Sorry.
I am not transparent. Wait.
All right. Let's thank Bjorn again and take a very brief break.
Okay.